Dear learners, a very warm welcome in the MOOCs of Energy Resources and Conversion Processes. I am Dr. Shweta Tripathi, Assistant Professor in Mechanical Engineering, School of Engineering and Technology, Indira Gandhi National Open University, New Delhi. Today we are going to discuss basics of solar energy. As we all know that solar energy is a renewable energy source and we are using it to generate electricity and heating purpose as well. How this energy is going to be converted into useful form, for that we need to know some basic principles of solar energy. The learning outcomes of this module is to understand the basic concepts of utilization of solar energy. We will learn the classification of solar radiations. In the end of this module, you will be able to estimate solar radiation on a horizontal surface. As we know that all the solar energy devices depend upon the electromagnetic radiation continuously being emitted from the sun and striking the earth's surface. These radiations are known as short wave radiations, and when solar radiation strikes the earth's surface, it gets absorbed and is re-emitted as long wavelength thermal radiation. Thus, thermal radiations are a form of energy emission and depend solely on the temperature and the characteristics of the emitting surface. Various forms of radiations differ only in wavelength, in the terms of wavelength only. If we study the spectrum of electromagnetic waves, the range of wavelength of thermal radiation is theoretically from 0 meter to infinite. A large part of thermal radiation has wavelength in the range from about 0.1 mu micron to 100 micron. Mu m, that is 10 to the power minus 6 meter. The visible portion of thermal radiation ranges from approximately 0.4 mu to 0.7 mu. As solar radiation passes through the atmosphere, some of it is absorbed, some is scattered, and the rest is reflected. Why? Because of the factors. Which are those factors? Air molecules, water vapor, clouds, dust, pollutants, forest fires, and volcanoes. The radiation reaching the Earth's surface is called diffused solar radiation, or simply diffused radiation. The radiation which reaches the Earth's surface without being diffused is called direct solar radiation, or simply direct insolation. The sum of the diffused and direct insolation is called global insolation, and atmospheric conditions can reduce direct insolation by about 10% on clear, dry days and by 100% on thick or cloudy days. Now let us talk about the heat transfer of the characteristics of the various surfaces, because the heat will be transferred in the process. So the thermal radiations are electromagnetic radiation, and they travel at the speed of light, which is equal to about 3 into 10 to the power 8 meter per second in vacuum. The speed of thermal radiation is related to the wavelength and frequency and is given by the relation c is equal to lambda nu, where c is speed of light in meter per second, lambda is wavelength of radiation in meters, and nu is frequency of radiation. It is given in per second or second inverse. The electromagnetic radiations have dual nature actually. They behave like waves and also like particles. As particles, electromagnetic waves are discrete quanta and called photons of energy. And in this case, E or energy is given by E is equal to h nu, where E is energy of photon in joules and h is Planck constant and is given by 6.6 into 10 to the power minus 34 joule second, and nu is frequency of radiations per second. Now let us see that what happens when a beam of thermal radiation is incident on the surface of a body. Following could be happen. Some of it may get reflected away from the surface, some of it may get absorbed by the body, and some of it may get transmitted through the body. So the radiation characteristic of a surface are its ability to reflect. Ability to reflect is known as reflectivity, and another characteristic that we talk about is it may get absorbed by the body. The ability to absorb is absorptivity and is given by rho. And third is some of it may get transmitted through the body. The ability to transmit is known as transmissivity and is given by tau. So alpha is reflectivity, that is that fraction of radiation that is reflected by the surface. Rho is absorptivity and it is that fraction of radiation that is absorbed by the surface. And tau is transmissivity and it is that fraction of radiation which is transmitted through the surface. So basically all the radiation either they will be absorbed or transmitted or emitted. So alpha plus rho plus tau is equal to 1. Total they will be 100%. Most of the solid objects that are opaque and their tau is hence 0 because they are opaque, so transmission will be. If a body absorbs all the incoming radiation, then what will happen? Tau will be 0, rho will be 1 and alpha will be 0. And such body is known as black body, which absorbs all the radiation. Absorptivity will be 1. The radiation characteristic of a surface depends not only on the surface property but also on the wavelength and direction of the radiation. The emissive power, we call it EB, of a black body is expressed by Stephen-Boltzmann law and is defined as EB is equal to sigma T to the power 4, where sigma is Stephen-Boltzmann constant and is given by 5.67 into 10 to the power minus 8 watt per meter square, and T is the temperature in degree Kelvin. Then comes the radiative properties of real surface. An ideal body is a perfect absorber as well as perfect emitter of thermal radiations. All real surfaces emit less energy if we compare them from the black bodies. And emissivity of a surface is the ratio of total emissive power, that is E of a real surface, to the total emissive power, that is emissive power of real surface to the total emissive power. So EB of a black body is called the emissivity and is given by E by EB. E is emissive power of real surface and EB is the total emissive power. The emissivity of a surface is generally a function of some parameters. What are these? These are surface temperature, wavelength of the incident radiation and direction of the incident radiation. And emission is defined as the average value over the entire wavelength range in all the directions and is called total emission. Now comes the Kirchhoff's law. What is this law for? It is for radiation. So the Kirchhoff's law of radiation states that the monochromatic means which has single wavelength. So Kirchhoff's law of radiation states that the monochromatic emissivity is equal to the monochromatic absorptivity for any surface in thermal equilibrium with its surroundings. Thermal equilibrium we had already discussed in our very first module in very first week. So we may express emissivity T is equal to alpha to T, where sigma is monochromatic emissivity at wavelength lambda and temperature T, and alpha is the monochromatic absorptivity at wavelength lambda and temperature T. We will learn later in this course that the solar energy absorbed by a solar collector is always in the process of losing the absorbed radiation to the environment by radiation, conduction and convection. It is highly desirable to make use of selective surfaces in solar collector absorbers to attain high solar energy absorption and at the same time to reduce radiation losses to the surroundings. What are these selective surfaces? As we were discussing that the radiation losses from a solar absorber can be reduced significantly when the receiving surface has selective radiation properties. If we talk about materials such as black nickel on nickel plated steel, then the short wave absorptivity is 0.95 and long wave emissivity is 0.07. If we talk about the material black chrome on nickel plated steel, it is short wave absorptivity is 0.95 and long wave is emissivity is 0.09. If we talk about black chrome on galvanized steel, then short wave absorptivity is 0.95 and long wave emissivity is 0.16. So generally for the selective surfaces, what properties we need? High absorptivity for radiation in the solar range of wavelengths and low emissivity for long wave thermal radiation. So these were some material that we use for the selective surfaces. So it is highly desirable to make use of selective surfaces in solar collector absorbers to attain high solar energy absorption and at the same time to reduce radiation losses to surroundings. So it is important to discuss the basic principle of solar radiation as well. So let us discuss first the basic principle of solar radiation. As we know that each location on Earth receives sunlight at least for a part of the year. The amount of solar radiation that reaches a particular spot on the Earth's surface depends upon various factors. And what are these factors? Geographic location. In Rajasthan, you will get more sunlight rather than Shillong. Then time of day. In the noon, you will be getting more solar radiation rather than evening or early morning. Then season, in the season, rainy season or in winters, you will not be getting more radiation than lowlands. How much solar radiation is reaching in that particular landscape, that is also local weather. What is the local weather? That is also important. So basically the factors that affect solar radiations are geographic location, time of day, season, local landscape, local weather. The sun strikes the surface at different angles and it ranges from 0 degree just above the horizon to 90 degree, that is directly overhead, due to nearly round shape of the earth. When the sun's rays are vertical, the earth's surface gets maximum energy possible. The more slanted the sun rays are, the longer they travel through the atmosphere and becoming more scattered and diffused, and it will reduce the amount of energy reaching the Earth's surface. Earth revolves around the sun in an elliptical orbit and is closer to the sun during a part of the year. When the sun is near the Earth's surface receives a little more solar energy. The Earth is nearer the sun when it's summer in the southern hemisphere and winter in the northern hemisphere. The 23.5 degree tilt in the Earth's axis of rotation is also a significant factor in determining the amount of sunlight striking the Earth at a particular location. The rotation of the Earth around its own axis is responsible for hourly variations in sunlight. In the early morning and late afternoon, the sun is low in the sky. Its rays travel longer through the atmosphere And at noon, when the sun is at its highest point on a clear day, what happens? The maximum amount of solar energy reaches a solar collector around solar noon. Let us talk about the nature of the solar radiation. The earth receives two types of solar radiation. We call it beam radiation and diffuse radiation. Let us discuss these radiations. Beam radiation, we call it direct radiation also. The radiation that is received by the earth without any change in the direction is referred to as beam radiation or direct radiation. That is, the radiation from the sun is directly coming to that particular surface. Then diffuse radiation. Diffuse radiation is received by the earth from all the directions. The radiations may change their direction due to scattering from dust particles, clouds, etc. All the factors we have discussed while passing through the atmosphere. Diffuse radiation do not have a unique direction. Diffuse component of solar radiation, that is shown in the figure by B, is that portion which is reflected from clouds, the ground and nearby objects, and the direct component of solar radiation. One is diffuse component, that is shown by B, and it is that portion which is reflected from clouds, the ground, and if there is any nearby object, then from that also. And the direct component of the solar radiation, that is shown as A, is that portion which falls onto the flat plate or flat plate solar panels, that is, which is falling directly on the solar panel. And the total radiation is the sum of direct radiation and diffuse radiation and is called global radiation or simply insolation. We call it insolation as well. And now, what is insolation? It is total amount of solar radiation per unit area per day that is reaching a part of Earth and is called the insolation. A short form of incident solar radiation is insolation. Solar insolation is defined as the amount of sunshine incident on the surface of the Earth per unit area per day. And you can determine the size of solar collectors provided that the value of solar insolation is known. If the values of solar insolation is less, the area of the collector will be large as compared to the case where solar insolation is high. Generally, this solar insolation is expressed in kilowatt hour per meter square per day, because the unit for solar radiation is kilowatt hour and we are measuring it in per unit area, so per meter square and per day. It is the amount of solar energy which falls on a square meter of Earth's surface in a single day. The rate at which radiations fall on the surface per unit area is called irradiance and is given by watt per meter square. If we talk about the engineering behind the solar energy, we come across the term extraterrestrial solar radiation and terrestrial solar radiation. In order to understand these terms, let us consider terrestrial and extraterrestrial region. Below atmosphere, it is terrestrial region, and above atmosphere, it is extraterrestrial region. Where CO in extraterrestrial region, what is there? CO, ozone layer is there, carbon dioxide is there, water is there, dust is there. So the rate at which radiations fall on a surface is called irradiance, and this we have discussed extraterrestrial region and terrestrial region. Generally, this diffuse radiation, long wavelength radiation, these are in terrestrial region. We know that the Earth is inclined at an angle and revolves around the Sun in an elliptical orbit. The orientation of the Earth's orbit around the Sun is such that the Earth-Sun distance varies only by about 1.7%. the solar radiation outside Earth's atmosphere is almost constant and is called solar constant. And what is this solar constant? The solar constant is the radiation received per second by a surface of unit area held normal to the sun rays at the mean Earth sun distance outside the atmosphere, and it is constant throughout the year. It is called solar constant and is equal to 1367 watt per meter square. The intensity of extraterrestrial radiation measured at a plane normal to the radiation is given by Duffy and Beckman in 1991. And IEXT, that is I is radiation, so extraterrestrial radiation is given by IEXT, and ISE is solar constant. So IEXT, that is extraterrestrial radiation, is equal to solar constant multiplied by 1 plus 0.033 cos 360 n by 365, where n is day of the year. So it is 1 for January 1 and 365 for December 31. Solar constant is defined as the solar radiation received per second by a surface of unit area held normal to the sun's ray at the mean Earth sun distance outside the atmosphere, and its value we had already told, that is 1367 watt per meter square. Now comes what are the main features of solar radiation. As we know that sun is continuously radiating energy in the form of electromagnetic radiations, and these radiations while passing through Earth's atmosphere are subjected to absorption by ozone, oxygen, nitrogen, carbon dioxide, carbon monoxide and water vapor, and scattering by dust particles, air molecules and water droplets, etc. in the atmosphere. So only a fraction of radiation striking the Earth's surface is reflected back into the atmosphere, where it is again absorbed and scattered. The remaining radiations are absorbed by the Earth's surface. The main components of solar radiation that are falling on the Earth are short wavelength, that are optical wavelength. Radiation from the sun reaches the top of the atmosphere. Clouds reflect 17% back into space. If the Earth gets more cloudy, as some climate models predict, more radiation will be reflected back and less will reach the surface. Then one important thing is that 8% is scattered backward by air molecules. 6% is actually directly reflected off the surface back into the space. So the total reflectivity of the Earth's surface is 31%, which is technically known as albedo. You may be wondering that what happened to the remaining 69% of the incoming radiation that doesn't get reflected back. If we break it up, the 19% gets absorbed directly by dust, ozone and water vapor in the upper atmosphere. This region is also known as stratosphere and it is heated by the absorbed radiation. 4% gets absorbed by the clouds that is located in the troposphere. This is lower parts of the Earth, and the remaining 46% of the sunlight that is incident on top of the Earth's surface, Earth's atmosphere, reaches the surface. Now let us evaluate the extraterrestrial solar radiation on January 1, June 22 and December 1 to see how much values will be different. As we know that for January 1 n is equal to 1, for June 22 n will be, add all the days, then n will come out to be 174. Then December 21 it is n is equal to 355. Now put on the equation which was IEXT that is I extraterrestrial is equal to solar constant into 1 plus 0.033 cos 360 n by 365. Put the values, solar constant take 1361 and put the values of n, and you will see that for January 1 we get 1412 watt per meter square. For June 22 we got 1322 watt per meter square, and for December 21 we got 1411 watt per meter square. Now let us estimate the average energy from the sun that reaches the surface of the earth. So what we have to know? The incident solar energy on the ground. Average over the entire earth it is 170 watt per meter square over a 24-hour day, and 8-hour summer day, and latitude is about 40 degree, so it will be 600 watt per meter square. So in this 8 hour we will receive 8 into 600 watt per meter square, so we will get 4800 watt hour per meter square, which is equal to 4.8 kilowatt hour per meter square. Now let us discuss the solar radiation on tilted surface, if the surface is tilted. So let us consider the solar radiation falling on a surface. The amount of solar radiation on a terrestrial surface at a given location for a given time depends on the orientation and slope of the surface as well. A surface which is always normal to the sun's ray would receive maximum amount of solar radiation. The solar energy collectors may be tilted at a suitable angle so that it is roughly normal to the sun's rays, so that maximum energy collection is obtained. If you wish to design any solar energy device, you need to know the data of solar radiation on such tilted surfaces. However, measured or estimated radiation data are available mostly either for normal incidence or for horizontal surfaces. It is necessary to convert these data to radiation on tilted surfaces. If you see in the figure, the IBN is beam radiation at normal incidence and IN is beam radiation at horizontal surface. IBI is beam radiation at tilted surface, and from this figure we could see that IB is equal to IBN cos Z, angle is Z for horizontal surface, and similarly IBI will be equal to IBN cos I. There the in tilted surface angle is I. If we talk about the beam radiation tilt factor, we give it by RB and it will be given by IBI divided by IB. It is ratio of the beam radiation, that is IB in tilted surface, to the beam radiation in the horizontal surface. So it will be IBI divided by IB, ratio of beam radiation at tilted surface to the ratio of beam radiation at horizontal surface. And if we replace it by the values that we had taken out, for IB it is IBN cos Z and for IBI it is IBN cos I, so it will be cos I upon cos Z. If we talk about the tilted surface, it receives diffuse radiation also as well as reflected radiation from the ground and surroundings in addition to the beam radiation. The diffuse sky radiation on the tilted surface at an angle is given by ID is equal to 1 plus cos S by 2, where ID is diffuse sky radiation on the tilted surface and S is the angle by which it is tilted. If the ground and other surfaces seen by tilted surface have a diffuse reflectivity of tau g for the both of the beam and diffused sky radiation, the amount of ground reflected solar radiation on the tilted surface is equal to tau g into 1 minus cos s by 2 times the of total radiation. And total radiation is sum of beam radiation plus diffused radiation on the horizontal surface. So the beam radiation, diffuse radiation and reflected components can be added to give the total incidental radiation, that is IT, on a tilted surface. So the total solar radiation on a horizontal surface, I, is the sum of horizontal beam and diffuse radiation. If we talk about the monthly average of daily total solar radiation on horizontal surface, how we will compute it? Generally, the computation of solar radiation either on horizontal or tilted surface is not an easy task. It requires complete knowledge of solar geometry and earth and sun relationships also. However, when the researchers have done on these subjects, various correlations have been developed to estimate the solar radiations at horizontal surfaces. So ultimately we need the value of monthly average of daily solar radiation on horizontal surface. So the correlation that is frequently used for determining monthly average of daily solar radiation on a horizontal surface is given by H by HA is equal to A plus B N by N, where AH is monthly average daily total radiation on horizontal surface, HO is monthly average daily extraterrestrial radiation on the horizontal surface. Small n, we know that it is monthly average daily hours of bright sun hours, and capital N is monthly average of maximum possible daily hours of bright sunshine hour. And A and B are regression parameters and are given by the correlations. In this correlation, phi and E0 are used, where phi is latitude and E0 is elevation of the location above sea level in kilometers, and N by capital N we already know. So these two correlations are used for calculating A and B. If we talk about the latitude and elevation of some of the locations, they are, we talk about Bangalore, the latitude is 12 degree 58 north and elevation is 921 meter. If we talk about New Delhi, it is 28 degree 35 minute north and 216 meter is elevation. Let us summarize whatever we have learned today. The major portion of the energy of thermal radiation lies in the range from approximately 0.1 μm to 100 μm. The visible portion of thermal radiation ranges from approximately 0.4 μm to 0.7 μm. Electromagnetic radiations behave like waves as well as particles. The electromagnetic waves are made of small discrete quanta which are called photons, and they travel with the speed of light. We have learned that emissive power of a black body is expressed by Stephen-Boltzmann law. The ratio of total emissive power E of a real surface to the total emissive power EB, that is of a black body, is called the emissivity of the real surface. We also have discussed that the monochromatic or single wavelength emissivity is equal to the monochromatic absorptivity for any surface when it is in thermal equilibrium with the environment, and this is the Kirchhoff's law of radiation. We have discussed that some surfaces have high absorptivity for radiation in the solar range of wavelengths and low emissivity for long wave thermal radiation. We have discussed that the radiation received by the earth without any change in the direction is referred to as beam radiation or direct radiation, and the diffuse radiation is received by the earth from all the directions. The radiation may change their direction after scattering from dust particles, clouds, etc. while passing through atmosphere. We have also discussed that the total radiation is the sum of direct radiation and diffuse radiation and is called as global radiation or simply insolation. Solar insolation is defined as the amount of sunshine incident on the surface of the earth. In our next module, we will discuss these radiation in the tilted surface, about solar concentrator, solar collector, etc. Thank you very much.